In this video, we'll be talking about navigation. Let's start by talking about what is navigation. So typically you start with a map, which is going to be a representation of your world. This task of mapping will usually generate either a 2D or a 3D map like the one you see here, which is known as an occupancy map. So this is a set of discrete cells that either tell you whether the space is free or it's occupied, like if it's a wall or an obstacle. The next thing you need to do is the act of localization. So that is to figure out where in the world your robot is. Of course, if you start your robot in a known location, you know where that's going, but then you also have to keep track of it as it moves around the environment. And localization uses the sensors of the robots. The most basic thing would be dead reckoning, which is just counting how the wheels spin to figure out how far you've gone. But there's a lot of problems with that. Often you also want to combine that with your other sensors, like laser scanners or camera, or anything that can give you basically some kind of correspondence with the environment you've already seen. Now, in robotics, usually these two things are combined into what is known as simultaneous localization and mapping, or SLAM. It's very often that to generate the map of the world, you're going to do this using SLAM because you never know the exact perfect position of your robot as it moves around and creates a map. And that's how we will create the map in just a minute. Now, once you've got this map set up, then you have, first of all, path planning to do. So if you want to go from a start position to a goal position autonomously, then you need a good way to figure out this path. And making a plan is one thing, but actually doing the path following, so executing that path in a way that's safe and reliable, is much more difficult. This is where having good localization is important because you need to know pretty certainly where you are in the world so that you can move along your path without going off into a strange direction or hitting a wall. And the other part of that is dealing with obstacles that you did not plan. For example, if there was a person that crossed in front of me here, would my robot be able to avoid that obstacle? Maybe wait for the person to pass or figure out an alternate route to take. So navigation is very challenging, and we're only going to do a couple of simple steps for this video. The first thing we need to do is collect a map. And we're going to do this completely using ROS. So if you follow your ROS guide for Turtlebot, you'll see that there are options of basically driving your robot around the environment, whether it's through your keyboard or with a controller like you see here. And once you're done taking a few laps around your map, you have something that you can then save to a file. If we then go into MATLAB, I've copied over these files, which is a PGM image file and a YAML file describing the parameters of the map. So basically how many pixels maps to what distance and what's my offset. And this is something I can now import into MATLAB. So if I go to the navigation folder, I have a function here called read YAML map, and that's where I'm going to start with. So let's do read YAML map of the file name, which is my testmap.yaml. And when I do that, it's going to create an occupancy map, which contains all this information. Of course, the most important thing we want to do is be able to display the map. So if I just do show of map, then here you see a figure window that contains my occupancy grid. And I can look around it, put little data tips here and kind of get a feel for what my world looks like. Now, this map is not perfect, but it'll serve the purpose of showing navigation. You see we've got a kind of a square hallway here that we can navigate throughout. So when I'm done with this, I'm going to actually save the map to a file called my test map so I can then load it later for navigation. Okay, so at this point, there's actually two workflows for doing navigation. You can do this all in MATLAB, or you can do this all in ROS, or some combination of the two. So we'll start with the MATLAB workflow. I'm going to go to the script called test path planning. And then here, I'm going to start loading my test map. Again, this is the same map that I just saved. No surprise there. And then in the next step, I'm going to interactively select a start and a goal point. So if I click a map, let's say I select a start point over here, and then I select an endpoint all the way out here. Then when I'm done, I can look at the next step where I create what's known as a probabilistic roadmap, or PRM, and find a path between the start and the goal. So actually, let me comment out this line for now, and I'll show you why. If I run the next couple lines of code, then here is going to be the result of my probabilistic roadmap. As you can see, the PRM basically samples a bunch of points in your map and makes a graph out of them. And then this graph is connected so that you can then search along it and find a path from start to finish. The problem with doing something like this is this has no guarantees on how close it comes to walls. So one of the options you can do is to inflate the map, as I'm going to do by uncommenting this line again. By doing this, I'm adding a buffer region, in this case of 0.2 meters or 20 centimeters, and I'm going to try replan with this new map. So as you see, now my walls are a lot thicker, and the idea is that my path will try to avoid walls a little bit more because now it can't go within a certain distance to the walls. So now that we have this plan, the idea is to follow it, and we'll see that through a live example. Now let's try to run this on the actual robot. So we're going to connect to the robot, and then here you'll see an occupancy map where I can select the starting and the ending positions. So supposing that my start position is somewhere around here, and my end position, let's set it somewhere around here, then the path planning should begin. Notice that right now we're only using the odometry of the robot. So the robot is currently just dead reckoning its way through, which means that it might actually hit into walls unless we have some better way of localization. For instance, instead of subscribing to the odometry topic of your robot, you could actually subscribe to the AMCL or Adaptive Monte Carlo Localization topic that's available as one of the TurtleBot demo ROS packages. So let's see how far this gets by just integrating its own wheel speed. And let's see if it gets around the corner. And as you see, the robot's missed its turn. Okay, so the other option is to use ROS. And to do this, we're going to use that test move-based action script. So this is going to take advantage of, if I connect to the robot, let me just execute this particular selection, then you see in my ROS actions, I can configure my TurtleBot to have this move-based action. And this is where I can set a goal pose, so X, Y, and its angle, so that the robot will autonomously use the map and try and move towards that position. And the good thing about using move-based is that it already has its built-in path planning and obstacle avoidance. So you will get something that perhaps works if you've collected a good map and you have a good localization estimate. I'm going to create what's known as an action client to this move base. And then in the remaining lines of code, I'm going to basically package up the message to move my robot, in this case, to this position, and then finally send the goal to the robot. Nice. So that's a little bit that you need to know about navigation. Again, ROS already offers some built-in navigation capabilities, and you can customize those, or you can do part of the navigation in MATLAB. It's up to you to choose, and all the best.